Suppose P is an odd prime. Let n be a divisor of phi of P. The solutions of x to the n congruent to 1 mod P include all elements of order k where k divides n. But since there are p minus 1 elements mod P, any elements left over must have a different order. So can we guarantee elements of all orders? Well, suppose phi of P is expressed as a product of powers of distinct primes. Then consider the congruence x to power phi of n divided by any one of those primes congruent to 1. This will have, at most, phi of P divided by Q1 solutions, and it will include all elements of an order that divide phi of P divided by Q1. So if there are any elements left over, they must have a different order. But are there any remaining elements? So if P is an odd prime, then each of the prime factors has to be at least 3. So when I divide by Q1, phi of P is P minus 1, and Q1 is greater than or equal to 3. So we can turn the equality into an inequality. If we make the denominator as small as it could be, that makes it larger. If we make the numerator bigger by multiplying by 3, that maintains the inequality, and we can remove that common factor of 3. And so this quotient is strictly less than p minus 1, which means there are elements that are not solutions to the congruence. So consider any element that's not a solution. Again, its order can't be a divisor of phi of P divided by Q1, so what could its order be? Since phi of P divided by Q1 is, then any element whose order includes a factor of Q1 to the n1, that is the greatest power of Q1 that divides phi of P, cannot be a solution to the congruence. So could we have an element of an order exactly equal to this highest power? So let A be an element whose order includes a factor of Q1 to power n1. Now if we're lucky and A actually has order Q1 to n1, then we're done. Suppose instead that A has order Q1 n1 times something else. So I can regroup that exponent as, and note that A to Q star can't be congruent to 1, since the order of A has to divide phi of P, which means that Q1 to the n1 times Q star has to divide this product of powers of primes, and since Q1 is prime, that means Q1 n1 has to divide Q1 to the n1, and so Q star has to divide the rest, and we can't have any factors of Q1. And so what that says is that the order of A to power Q star must be a factor of Q1 to the n1. But it can't be Q1 to the n for any exponent less than n1, since then it would have shown up as a solution to our original congruence. So it must have order Q1 to the n1. And this proves that if P and Q are prime, where P is assumed greater than or equal to 3, and Q to the n is the largest power of Q that divides phi of P, then there's an element mod P with order Q to the n. So it's useful to consider the consequences. We can take this one step further. Suppose A does have order Q to the n. Now we can break that exponent apart, and as before, this internal expression can't be congruent to 1, since, by assumption, A has order Q to power n. Which means that A to power Q to the n minus who cares what must have an order that divides Q to the I. But it can't be anything less than Q to the I, since then A wouldn't have order Q to the n. And so that tells us that if P and Q are prime, again P greater than or equal to 3, and if Q to the n divides phi of P, then there is an element of order Q to the n. So let's try to find an element of order 4 mod 97. Since p of 97 is 96, which is 2 to the 5th times 3, we want to find an element of order 2 to the 5th. So we note that 2 to the 4 times 3 is 48, so not quite the highest power of 2. So let's consider the congruence x to the power 48 congruent to 1. Solutions to this congruence will include all elements of order, but no element of order 32. So we look for a non-solution, and we find that 5 to the power 48 is congruent to 96, so 5 is not a solution, which means that 5 has an order that's a multiple of 32, and importantly, it's a divisor of 96. So its order is either 32 or 96. So either we have 5 to the 96, well that's 5 to the 3rd to the 32nd, where 3 is not congruent to 1, or 5 actually has order 32, and so 5 to the 32nd is congruent to 1. And we do find that 5 doesn't have order 32, but 5 to the 3rd, that's 28, does have order 32. Now, since it has order 32, we know that 28 to the 32nd is congruent to 1, where 28 has order 32. We also know that 28 squared to the 16th is congruent to 1, so 28 squared has order 16. 28 to the 4th to the 8th, also 1. So that means 28 to the 4th has order 8. 28 to the 8th has order 4. And then we have 28 to the 16th has order 2. And so not only can we find an element of order 32, we can also find elements of order 16, 8, 4, and 2. And so now we're ready to answer the question, do we have primitive roots mod p? Well, first of all, if p is 2, then phi of 2 is 1, and 1 itself has order 1. So clearly, primitive roots exist if p is an odd prime. Remember, 2 is a very odd prime. Meanwhile, if p is an odd prime, then phi of p will be a product of prime powers. The preceding shows that if pi to the ni is the largest power of pi that divides phi of p, there is definitely an element xi with order pi to the ni. Since the pi's are distinct, this means that the product of those elements will have order, which is phi of p. Consequently, if p is an odd prime, there exists at least one primitive root, mod p.